was amazing meeting all these people from all these places who've been facing similar problems as me or as the company. And it's nice just talking to people in the hallways after the talk, during talks, between talks.
Okay then, I think I start. Welcome everybody to my talk named Vectorizing a CFD code with standard SIMD supplemented by almost transparent loading and storing. My name is Olaf Krzikalla and I work at the German Aerospace Center, more specifically at the Institute of Software Methods for Product Virtualization. So you see, we love long titles, be it the name of the institute or be it the name of the talk. Yeah. Okay, speaking of the talk, what's the motivation of the talk today? Well, in the beginning, there was a task. And the task was to vectorize a scientific code. This scientific code has a huge code base. And so it was something somehow out of question that only an evolutionary approach was feasible. I couldn't change it all, just small parts of the code. In the end, it is like, here you have the code, please vectorize it, please optimize it, but please don't touch it. Yes? So, yes. So I got, with these constraints, I got an idea. Especially how can I load and store variables in SIMD registers in a manner that it looks like naturally, that it looks very naturally to a C++ programmer. And that was the idea, and then I figured out that I can generalize this idea. And so the idea to this talk was born. And in this talk, I will take you on a journey about my experiences with the vectorization using standard SIMD. And I also want to introduce the SIMD access library, which has been created during this journey. Okay, let's start with some background about vectorization. I guess everybody is somehow familiar with vectorization today. Basically, your CPUs are capable of using one instruction and operate above or operate with multiple set of operands with one instruction. So this is the term single instruction multiple data, or short SIMD. And for more details about vectorization and especially about standard SIMD, I recommend you the talk of Matthias Kretz from last year CppCon. All the links I will give you on the slides, you will find all these links also in the Discord channel. I have put it up before the talk already. Okay. Back to the vectorization. In the most simple case, or most of the time, if you vectorize, you want to vectorize a loop. Yeah? And here we have a very simple example. You have a simple loop, and you somehow want to transform this loop so that the variables are more or less stored in SIMD registers, and also the operations are now SIMD operations. Yeah, so, and this loop transformation is this vectorization, and this vectorization can be explicit, guided, or implicit. The best way to do it is implicit. The compiler does all for you. Then we have a guided implementation if you use OpenMP Pragma, for instance. And if this all fails, then you have to switch to explicit vectorization. And at this point, I just want to give a short introduction to the scientific code where I have applied the vectorization to. It's called CODA, and it's CFD for ONARA, DLR, and ARPUS. CFD, Computational Fluid Dynamics. Computational Fluid Dynamics is a notorious task in HPC computing. HPC computing means you want to exploit all levels, all parallelism levels available. That means distribution, threading, but also data parallelism, instruction level parallelism as provided by SIMD. And I've picked a particular task of the computational fluid dynamics. Here you have a cube of points, and you want to compute the flow in the cubes between the points. And you see there's a deeply nested loop here. It's 5 levels. The first loop iterates over the direction, and then we have the coordinates, and in the end, we iterate over the edges. Yeah? And the first thing here, which is good to know, is that the inner function, which we call here the compute flow, is heavily compute bound, and this means this is a worthwhile vectorization target. On the other hand, it has a lot of cascading calls inside this function. Partly it ends up in external libraries, namely eigen. Also, in this function, there are data structures created, they are passed to other functions, and they also are returned. So in the end, it was clear we have to use explicit vectorization here. Neither OpenMP nor the compiler itself was able to vectorize this. On the other hand, this first loop means we compute the flows in every spatial direction of this cube. What this actually means is that we iterate over the cube points in different directions for each direction in a different order. And this also means that reordering the loops or rearranging the points at the beginning of the actual computation in an area of structure of array way, it's not really viable because you then have it ordered for one direction but not for the other two, and then you have to reorder it for each other direction. So in the end, the data layout remained just scalar, and we just have to reorder or reorder the points on the fly, the data on the fly for the SIMD computation. This is already the loop after a rearrangement, so that the inner loop is feasible for vectorization. Now we have fused 2 loops together so that we always compute the flows over a plane. In this case here, it's the AJ plane, but in a later direction, it's the IK plane, for instance. And what's also important here is that now the nested loop, the C loop, the mostly nested loop here, the length of this loop is now invariant to this loop, to this V loop. So we can vectorize this V loop without taking care of the length of the most inner loop. And on the other hand, now since size could be rather small, sometimes even values of 3 are possible, now the loop becomes sufficiently large to be worthwhile to be vectorized. So the only task now remains is we have to vectorize the loop body, so in a manner that it keeps it's still readable, that it's still recognizable, and then since size is not necessarily a multiple of the SIMD size, we also need a scalar version for residual loop computation. Yeah? And of course, it's the best to have a variant or a syntax where we have which can deliver us a SIMD variant and a scalar variant at the same time. Okay, so let's talk about the vectorization of the loop body. This is now the line of the introductory example, and we just start with an operation. How do we tell the compiler that we want a SIMD operation here? And this is rather simple, because if you assume that the SIMD values around this operation already carry some kind of type information about the vector type, or the SIMD type, then we can just use C++ operator overloading, and then the compiler will do the right thing here. It selects just the right SIMD operation for us. This is already provided by nearly all SIMD libraries. By all I'm aware of, but maybe there are some more out there, especially also by standard SIMD. Okay, now the question remains, how do we get the SIMD values from our arrays and from our integer, from our index? And this is not so easy to do it implicitly, because we have no vector type information in the x, y, z, which are just pointed to doubles, and in I, which is just an integer. So we need some explicit load and store operations. Again, this code is not particular targeted to any SIMD library here, but this is how it always works. You need explicit load and store operations, and which means if you have a scalar loop body, then you have to rearrange the loads and stores of your variables, and somehow have to rewrite the loop body. And also it also means that the scalar version looks very differently. Yeah. So just let's iterate in a more general way. If you have a loop body, then you can separate it in 3 steps. You load some variables, or some SIMD variables, you perform some SIMD computations, and in the end, you store your results. Yeah. And now, what also is the case is that the scalar versions of your loop usually intertwine the loading, the computation, and the storing in one expression. Yeah. On the other hand, what is also true is that we already can perform the SIMD computations by using the type deduction, similar to our scalar version. But what we actually want is performing all these steps in a SIMDized way, and use a type deduction somehow from another level. And now, if you look at this picture, you might already know where I am heading on, because the only variable which is above the type deduction here is the I, it's the integer. And that's the core idea of my approach to SIMDize or to vectorize a loop body. I encode the SIMD type information in the loop index. That means if I is a SIMD index, this is just a newly introduced class, then the SIMD version, a SIMD version of the variable is loaded. If I is just an integral type, for example, an integer, then it just falls back to the scalar version. And then, of course, the loaded types are deduced by the SIMD index, and then the deduction propagates forward, and you end up with also a proper SIMD operation here. Okay, the only thing we now have to do is, once we have our SIMD index class, we have to overload the bracket operator, the second argument of the bracket operator, and then we can write this loop like before, this loop body like before, and we are just done. Yeah. We just need a SIMD index and an overloadable bracket operator here, overloaded bracket operator. Well, you might know there's a small detail here left out, and this is that the bracket operator is not yet globally overloadable in C++. And unfortunately, there's currently no general solution, since index is the second argument here. The possible workaround, the workaround I came up with, was to use a macro at this point. I called it SIMD access. And this macro just delivers you a SIMD type, but you can also store a SIMD type in a SIMD access L value. In this point, yes, I have to rewrite the loop body. I have to put the SIMD access macro everywhere where I want to access a SIMD variable, but I don't need to rearrange it. I can keep expressions, operations, and loads and stores intertwined in one expression. The second thing is that now I can write the same code for the scalar and vector versions, because the SIMD access macro also works with an integer type. And this is a basic idea of my SIMD library. You find it on GitHub, or you can find it on GitHub. And it is a supplement of standard SIMD, standard experimental SIMD for the moment. The names reside in the namespace SIMD access. And it's more or less meant as a proof of concept how SIMD indexing can be done. Yeah. Its implementation is demand-driven for the moment. So whenever during my vectorization journey, whenever I have found a feature which I needed and which was generalizable, then I have put it in this library. And it also can serve as a platform for experiments and discussions of future developments regarding this idea. There's also a single header file included, so you can include this in Godbold just without or just very easily. Okay, so now let me introduce the basic features of the SIMD library, SIMD access library. The first is a type, the SIMD index type. And we have 3 index types here. The first one is just called SIMD index. And it's this index just defines a consecutive sequence of elements which starts at a given index. Yeah? Each of these SIMD index types have a template parameter which defines the SIMD size. Yeah. The second one is just a standard SIMD with an integral value type, which can also be used as a SIMD index, and it then indicates the elements indirectly. Yeah? So every value in a standard SIMD is an index to your actual data array. And the third is an index array, which is like a standard SIMD, defines an indirectly index or denotes indirectly indexed elements. However, in this case, the index array can hold a pointer or an iterator to a larger array of indices, which then, so you can have an array of like 100 indices and then point in this array at a certain point and then have a SIMD-sized range of SIMD indices. Now, we have some index types. How do we use it? You already know this macro, this SIMD access macro. It's just a replacement for this expression here, array bracket index. And index can be either a SIMD index or it can also be a scalar version. My implementation here currently expects a continuous array and the element 0 should exist or should be valid. But there are other implementations thinkable which don't come with these restrictions. You can also, I already have mentioned it, you can use the SIMD access macro also as an L value. That means that SIMD access by itself doesn't give you a SIMD type, but an internal type, which has an operator for SIMD, but sometimes you want it more explicit, that you want to have a SIMD value, especially, for instance, in deduced context. Yeah, when you have a template which expects a SIMD, you can't just call it with SIMD access because then the template is try to instantiate it with internal type, but what you actually want is the SIMD type, and then you use SIMD access v macro in this case. As an extension, you can give an additional expression to the SIMD access macro, and with this you can also SIMDize submembers or members of your actual variable. So I give you here some examples. So if you have an array of elements and each element is by itself an array of 3 elements, then if you want the first element of each of these array elements, then you have to write it like this. If you have an array of pairs, for instance, and you want to access the first element of each thing, of each array element, then you just put this dot first as expression there, and you also can combine this and reach sub-arrays or members of data members and so on. Okay, now we know which index types we have, and we know how we can use it. How do we get it? The library provides you a function which is just called loop, and the loop here, this version, just iterates over a consecutive sequence from start to end, and calls a functor. And this functor is a generic one. It is either called with an index SIMD size with a linear index, or for the residual iterations, it is then called with a scalar index. We have also a function, a loop function, which works over random access iterators, and this you use this kind of function if you want to have, or if you have an indirectly indexed sequence. Again, the functor is a generic one. It's either called with an index array, or it is called with an integer for the residual loops. So, and if we put all these basic features together, we already are able to vectorize our simple function, our simple example function here, in a way that we just need to rewrite the SIMD accesses, but nothing else. Yeah? And this also handles scalar loops and vectorized loops in the same way. So the expression, the syntax is the same at this moment. Okay, these are the basic features. Now I come to the extended features of my library, which we needed during the development of, or during the vectorization of our code. The first one, reflections. Okay, you have heard a lot about reflections already during the CppCon. My approach was not so general, it was more pragmatic. But let's see. First of all, consider this example. Now we still add elements together, but not doubles, but points. And points have the usual operator plus overload here. And on the right-hand side, you see the table. In the table, what actually happens, you have 8 additions performed. And what you actually want, if you vectorize this loop, is to perform only 4 additions. Now this is an example where we have a SIMD size of 2. And so that the points are shrink together. So the first 2 points, the x1 and the x2, are loaded in one SIMD register. Then the y1 and y2 are loaded in the next SIMD register, so that we at the end only have 4 additions, 4 vectorized additions to perform. And how have I achieved it, or how have we achieved it? in order to get it working, you need two functions here. The first one is a recipe how to create a simnized value. And it's called simnized value, and it takes a point and returns a point which with simnized members. So here note the recursive implementation. In this case, the implementation uses, or the example uses, computer template argument deduction. So the point here is also templated, and the simnized values of the data members of the point then determine the template of the point, which is then returned by simnized value. In this case, the library already provides you with simnized values for fundamental types, for arithmetic types, and return the appropriate SIMD types. And in this point here, the point would be instantiated with a SIMD version of double under the assumption that the original T is a double. The second function we need is a access function. This access function uses or takes a functor, and then this functor is recursively called, again recursively here, called for all data members inside the structure for which we need this reflection. And that's all we need. Here's a complete example. You see this block of code where we have this information to the compiler how a point can be simdized to a SIMD version of the point. And then we end up exactly with this line. And this works. You can just try it out on Godbolt, as I said before. You find the link also in the Discord channel. Okay, a next feature which we thought or which we have found useful was the introduction of a universal SIMD class. Consider this code here. In the vectorized loop, we have an access to some data which is not indexed, but this is rather an opaque function. It delivers us some data. This data can be a complex struct, and maybe only a few members of this struct are actually used, and maybe the struct is then accessed even in inner loop. So what you don't want is rearrange all these statements here. For instance, you don't want to move the generate call in the loop, in the inner loop, because then it gets called too often. On the other hand, you can't just use a SIMD access here, and you can't use, or you don't want to SIMdize the point struct, because it might be too much. And at this point, I have introduced a universal SIMD class, which is basically a standard array with two additions. The first one is a static size function. That's interesting because the usual or the standard array itself has also the size function, but it's not static. Could be easily static. I don't know why not. And the second is a constructor which is similar to the constructor of standard SIMD, where you can generate all the elements using a functor, and this functor then gets passed, or to this functor, integral constants are passed for each element to generate. And then I have introduced a function, generate universal, and you give this function an index, which then can be a SIMD index. It can also be a scalar index. and a generator, and then you get a universal SIMD. And if you apply this to our code, then it looks like this. In the original code, you have this data generate call, and you find this data generate call also in the generator of the universal SIMD generator here. Okay, so we have this point now. Of course, if you want, sometimes you don't have structures, but just references to structures. And then you also want to store only references to your universal SIMD. And at this point, you have to use standard ref or standard cref in your generator. Once you have your universal SIMD, you can access it very similar to the standard to the SIMD access macro. We have introduced a SIMD universal access at this point, and you have a value which is either universal SIMD or a scalar variable, and again an expression which is then concatenated to the value. I show you this example here. Usually, or in the original code, you have this point.getVelocity, and in the vectorized code, you have this SIMD universal access, and again this dot get velocity j as a second argument of this SIMD universal access call or macro. Okay, the next extended feature which we have introduced, or for which we have to introduce some things in our library, handling of conditions. Here you see an excerpt of actual code of which we have vectorized, and this is how I vectorized it in the first version. I just compute a mask, and then if any bit in the mask is set, then I take the first branch, and if at least, or if not all of the mask bits are set, then I also have to compute the second branch, and in the second branch I then store to the result only those elements which are not masked out. The vectorization of this code was done with the assumption that the time, if I compute all vector lanes, this is more or less the same time, or that will consume more or less the same time as if I compute just one vector lane. So I just compute always all vector lanes if at least one vector lane is requested. Now let's take a look at this log call here, because, well, if you take a look at Godbolt here, then on the left-hand side you see just a log call for a SIMD variable, and on the right-hand side you see the assembly output, and what you see here is that at GCC 14, even at GCC 14, the log call is unrolled. So the assumption that the time for one vector lane is the same as the time for all vector lanes doesn't hold at this point. Yeah. The same, I've seen the same behavior with Clang. The only compiler I have tested which does it different is the Intel compiler. It calls an SVML version. However, I don't know what this version internally does. Maybe it does it fully vectorized, but maybe there are also some serialized or unrolled computations. In the end, I ended up here with a pragmatic solution. I just had to introduce a mask log function, which indeed then just call the logarithmic function only for those lanes where it's actually used. Yeah. Okay, Now in this slide you already may notice the SIMD members, and this was the second thing I had, or where I had to extend the condition handling. I had to introduce a new where expression for SIMDized structures which are not pure SIMD types, so which are not just standard SIMD types, but extended SIMDized types like our point, SIMDized point. And here I need a where call and a where expression, and this where call then returns a where expression, which then mimics the standard where expression. However, it internally uses this SIMD member call again, so you can use it for more complex variables than just standard SIMD. This also means if you handle or if you use this in your code, in your actual code, and you know that your T is, in this case, the template parameter can be something else, but standard SIMD, something other things, SIMDized structures, then you have to use these using directives so that the compilers can always select the right one, where expression at this point. Okay, so far to the features of the SIMD access library. I now come to some possible extensions which I have thought of during the development. And the first one is support for getter and scatter instructions, or getter and scatter variants of the standard SIMD constructor or storing operations. Just consider this small piece of code here. Again, we have a point which has two data members, x and y, and we access the first data member x here. And what internally happens here is that this SIMD access finally resolves to a call to a function called linear load. This linear load knows that it operates over a linear index, and it can do all these computations. The element size, by the way, is size of point, and it then uses the generator constructor of the standard SIMD. However, you could also at this point think of a version where you just use a guesser function, because at this point you already have all the information available you need in order to use a guesser function. The thing is, on the right-hand side we have the SIMD access. On the left-hand side, on the left-hand side we have the SIMD access version. On the right-hand side, I have given a version where we have a guesser, an explicit guesser function, and if we measure this, we see that the guesser function is much slower than our SIMD access macro at this point. And these are the assembly output for both loops. So you see, actually, the compiler in both variants do what they should do, or what it should do. Yeah. So what are possible reasons for this slowdown? First, the address computation on the left-hand side is immediately done. On the right-hand side, the CPU has to somehow do some register addition internally. Then the second thing is that the left-hand side uses actually two registers to load the SIMD variable, and this means it can use some out-of-order execution. On the right-hand side, it purely depends on the implementation of the guesser instruction inside the CPU, which we don't know how optimal it is already. And the third thing is that currently the CPUs have there's a vulnerability. Oh God, it's called downfall, and that's why all guesser instructions are throttled in our recent CPUs. Maybe this situation improves in the future, but for the moment, guesser and scatter support would be a nice to have feature in standard SIMD, but it's not that urgent because we don't get any performance out of it. Okay, another possible extension of C++ is a globally overloadable operator, a bracket operator. This would be, in our case, the signature of this operator. It just takes any base operand and then SIMD index as a second argument, and with such operator overload, we would be able to already write loops like this, which are then very accessible again and very readable. Yeah. This is, by the way, not a new idea. This is discussed everywhere and then. I have given you here a link to a paper where it's mentioned, but if you look at the internet, you will find this question often. The SIMD access library provides 3 workarounds for this problem. The first one is a named function. This named function is there just to prove that it is possible to write such an operator with exactly this signature. Yes. The second one is the SIMD access macro. You already know this. And the third version, if you have a class, if you not just operate over a simple pointer area of doubles, but actually have a class, and you can inject the index. You can inject such an overload to this class by using the index operator class, which is also provided by the SIMD access. And then, well, if you have a standard vector, you can just access this vector or this vector with this injected overload, like here, in the very natural way. You see this line here now is as you would write it for scalar code. Okay, now I will go out on a limb. What if we would have overloadable dot operator, so that we have the ability to overload on member accesses? Such an operator could look like this. And if we would have this, we could write all our SIMD expressions like this below in the most natural way possible. Yeah? So no macro is needed anymore. The technique I think could be used at this point is that the member is deduced by the compiler. However, the compiler must know the type of the object at the point of the access in order to enable the compiler to look up for the appropriate member name in the expression or in the type of the object. Yeah. Then the compiler is able to resolve this template, and you have this kind of an operator. Yes. SIMD access also provides some workarounds for this thing. First, again, something like a proof of concept, yeah? A named operator called dot, of course, which, however, takes this pointer to member explicitly. Then, of course, the second variant is the SIMD access macro. And the third one, it's not really provided by the library, but it's you can find it in a test in the library, is using kind of named index variables. You have an array of named indices, and then you have a structure or a tuple of user-defined structures, and then you can access these the variables by using these types, these named types. Okay, so far about possible extensions I could sort of if standard SIMD and SIMDization, or to make SIMDization, vectorization even more convenient with C++. Okay, some results. First, we have some software engineering results here. In the end, in the code base, about 200 lines of code were changed. It's now a little bit difficult to show you this, because the code itself is export restricted, so I can't show you the source code here. You have a little bit, that's a little bit, well, trust me. We are in a trust me area here, yes. Most of the code of these 200 lines, we have, for instance, this loop arrangement, rearrangement there. We have this mask locked, which is also some lines of code which have been added. In the end, like 20 lines in the actual loop body were changed, where you have to put the SIMD access or SIMD universal access macro in. Yes. The expressions, the control and the data flow all remains the same, more or less. Then I had to add like 220 lines for the reflections, for the SIMD value and SIMD member functions. But these are outside of this code, of the actual computational code. So an engineer is looking at its CFD code, don't see these lines. Then I had to patch the eigenlibrary, and you see, obviously, what I had to do here, I had to introduce, or I had to generalize the comparison operators. They use to return only bool, but they have to return auto in order to be enabled for vectorized instantiations. And of course, at the end, I also had to add the lines of code of the SIMD access library, which I have developed doing the vectorization. In the end, I have to say it was a lot of initial effort, but once I have done, the vectorization went very smoothly afterwards. Yeah. Then this is a talk about vectorization, so I have to give you some performance results, of course. You see now some numbers, and you expect some numbers, but you won't expect the numbers I give you here, because what you see here is the speed up number, that is the vectorized version, the time of the vectorized version divided by the time of the scalar version. And we have vectorized for AVX2, we have a data type double here, so that means we have a native vector size of 4. That means in the ideal world we would have a value of 0.25. And if we have a speed hub, just any speed hub, we would like to have any value below 1. But what you see here are that actually our SIMD version slows down with AVX2. Okay, admittedly, Skylake and Broadwell are rather old processors, and there's a reason. Of course, first of all, if you SIMDize your structures, you have some overhead. Yeah? But you have this overhead anyway. But there's another thing here. We have measured just the instructions on various CPUs, and what you see here is especially the division on Broadwell uses just 4 times for the vector version versus 1 time for the scalar version. So this what internally happen here is that they only have 1 division unit, and they just use a scalar division and iterate internally over over all 4 values. So the thing we have to learn here is single instruction in SIMD. Single instruction does not mean a single time step. It just means a single instruction. And the CPU internally may do some unrolling, and then you might end up, you might experience a slowdown where you don't expect it. So this is disappointing. However, there's some light on the horizon because standard SIMD has a nice feature. It's an unrolling feature. You don't need to stick to your native vector size. You don't need to have the vector size of 4. You can, for instance, use a vector size of 8 here. Just double it, and all of a sudden, we all other things being equal, we get an acceleration here. We get a speed up, and actually, this is reasonable. It's a reasonable result because your algorithm uses some number of vector registers to compute. And if you unroll it, it will use the double amount of vector registers, which then enables the CPU again to do some out-of-order execution. Yeah. So keep this in mind. Unroll and try it out to unroll your standard SIMD code. It often gets better. It, of course, depends on the algorithm. Yeah. In our case, a factor of 2 was a sweet spot, more a factor, so unrolling for 12 or even 24, size 12 or 16, didn't help us anymore, just because in our case, the algorithm was so complex that the compiler started spilling registers, vector registers, if you unroll too much. Okay, but that's one of the things we have learned, and that's now where I conclude my talk. I want to conclude my talk. And about the lessons we have learned. First one, standard SIMD is up and running. I have talked now for 40 minutes about a lot, how I use standard SIMD and how you can even extend this. What I haven't talked about yet are the problems I had with standard SIMD itself. Yeah? The thing is, I didn't have any. Yeah? I just used a recent GCC compiler, activated C++20 mode, included standard experimental SIMD, and it just works out of the box. So yes, standard SIMD is there, it's up and running, and you can just use it. Okay. Also, compilers makes a decent optimization job. My macros and all these layers I have put around are full of compile time switches and lambdas, but in the end I have never seen any artifacts left in the assembly code. Yes, and the second thing, multiply your native SIMD size with a factor, which always depends on your algorithm, so to squeeze out as much performance as possible. The second thing we have learned is if you vectorize conditions, be careful. Unused lanes may consume time, even at points where I don't expect it. And the third thing I have learned for myself, use my library, because then vectorization becomes much easier. Yeah. Also, use auto everywhere possible, because if you have somewhere struct with a particular type, at one point you end up with, oh, this could also be a symlized struct. Yeah? We have seen this on this eigenpatch, for instance. Okay. But yeah, in the end, the vectorization was smooth sailing once I have all the features up and running in my library. So some outlook, the SIMD access library is still in development. As I said, it is demand driven, so it's not feature complete yet. And I also think that the reflection API could, I could do some work, put some work on it, maybe there's a better approach than the one I have, which works, but it's very pragmatic. But maybe at this conference I also have some inspiration. I also get some inspiration for this. And then there's some discussion which we could do about a globally overloadable operator here. Maybe there's some interest in the topic. And the last point, yes. What about an overloadable dot operator or member access operator? I think technically it is possible. In my case, in my use case, a counterargument might be that it just hides too much complexity in the end, because you end up your expression looks very naturally, but you end up with a gather operation, for instance, or scatter operation, or even some more complex. So I don't know. Maybe in a future version of C++, this becomes more interestingly. So that's it. Thank you for your attention. And if there are some questions, then now it's time.
Hi, great talk.
Thanks.
I'll point out one thing and then I'll talk about the overloadable operator square brackets.
Yeah.
But first I just wanted to say you picked a very difficult problem because you weren't allowed to reorganize the data structures. And so it's pretty extraordinary that you got speed up at all. So good job.
Thank you. To say this, I hope that we get even better speed up with more modern CPUs. The CPUs I have tested on a local workstation, but we have also a cluster with the Zen 2 processors. And if you just remember the numbers on the Zen 2, it really looks good.
Yeah.
The Zen 2 really does a good job. However, this is a cluster for aircraft engineering, and aircraft designers are a rather conservative folk. That means getting a C++20 compiler up and running on this cluster is a little bit difficult for the moment. So we will get results in the future, but not for the moment, sorry.
That's okay.
But yes, I hope that we then get a better improvement.
Yeah, just to address the operator square brackets.
Yes.
So the only reason we didn't attack that in the paper is because we wanted to make, well, first of all, we really wanted to get multiple arguments through C++23.
Yes.
And that wasn't so hard to do, but permitting a global overload of operator square brackets was a much more radical change, and we didn't want to try to do those two things in the same paper. So it's not that we're opposed to the idea, it's just that it was a bigger, more impactful change, and we didn't want to try to do that in the same paper. So I'm not opposed to the idea.
Okay.
Yeah.
Good to hear.
Yeah.
I mean, there are different possibilities. You can have a globally operator, but you can also use this, how it is called, where you have this, so deduce this.
Yes.
Now, and then say, but this deduce this is now my second argument and not the first one. Currently, it's always required to be the first one. If it's the second one, I haven't thought it through.
Yeah.
Maybe this is just, I don't know if this works out in the end, but this is also a possibility to have this, or to mimic this globally overloaded operator, because you can just put this operator in the SIMD index class and then just say, my deduce this is the second argument, not the first one. You understand? The first argument is something else. As I said, I don't know if it works out, but this is another maybe approach.
Okay, thank you.
But I think using the globally approach using the global approach might be the way to go.
Thank you.
Thank you. Okay, no further questions? Then thank you again for your attention, and then have a nice evening.